the received baseband signal model. I mean, it's very, very important because, you know, this is mainly the way that we will express the baseband received signal. So a symbol, so we have a symbol, okay, multiplied by a channel complex gain, and when you see something like this, and you don't see a summation or integral or something like this, it does not mean that there is no multipath fading. There is multipath fading. It may actually be significant, but we are basically operating under the flat fading channel model, which is called the frequency non-selective model. And in that model, basically the delay spread is much smaller than the symbol duration. And so, you know, if you start with something like this, okay, 2 by f doubler tau d tau, you know, you can justify basically taking this outside the integral and giving it some sort of, you know, average delay or something like that, some constant here, and then putting the integration here, and this will be g of t, which is this h here. Okay, so we are doing flat fading, and without flat fading, you have intersymbol interference, and now you know from the homework, you know, how we deal with intersymbol interference. Intersymbol interference means that you have a stream of symbols, okay, and now you will basically have a channel filter, channel multi-tap filter. Okay, and so this is the baseband model, and so what you get here is basically the symbols convolved with the channel, convolution. So like in the homework problem, you get that the output is like, you know, yi is equal to si plus 0.5 si minus 1. So that's a two-tap filter. It's as if we convolve the sequence of input symbols with a filter with a coefficient 1 and coefficient 0.5. And if the delay spread is much larger than the symbol duration, basically you have many taps in your filter. So what do we do to solve this problem? Okay, you know, how can you do detection here? So the idea is that you take your symbols again. You know, they go through the channel, and then what you do here is an equalizer. Okay, and so the equalizer is basically sort of the inverse transfer function of the channel. Or you can think of the equalizer as a process of deconvolution. Like you have two sequences that are convolved together and you want to deconvolve them. Okay, and so, you know, examples like the zero forcing equalizer, the LMMS equalizer, in which like you get an estimate for a particular symbol, and then you detect that symbol without worrying about the other symbols. Okay, so again, there is an important component in communication systems, wireless communication systems, which is the equalizer. So the equalizer, again, you know, it's sort of a process of deconvolution in which you try to basically remove, you know, this mixing of the symbols. Okay. Now, OFDM, which we will study later, and is like sort of the main part, you know, the most important, with MIMO, the two most important topics in this course, OFDM can be thought of as an equalizer. Okay, so it is, but it is an equalizer that is sort of, you know, a bit different from zero forcing and from LMMS that you have read about in for homework 2. So OFDM is like equalization, doing equalization in the frequency domain. So like the process will involve also taking the Fourier transform and inverse Fourier transform. We'll see it exactly later. But the OFDM is an equalizer. In fact, OFDM is nice and very useful because it is an efficient equalizer. It's not just an equalizer. It is an efficient equalizer, and again, let's talk about this later. Okay, so so this problem again gave you you know, a feeling of what it takes. Like if you have intersymbol interference, if you don't have a flat fading model, you will have to use some sort of an equalizer. Okay, and this can be like a sophisticated equalizer like OFDM, as we'll see later. Okay, flat fading, for flat fading, you know, it's like the channel filter is just a single tab filter, which I mean, you don't really need to use the word filter. It's like your signal is multiplied by G of T. So the channel is a random process, but if you fix an instant of time, you know, you extract a random variable. And so here we are writing H, not H of T, because we are actually pushing this further and saying, you know, if basically the symbol duration is much smaller than the coherence time of the channel, okay, so if the sim, you know, basically if the symbol, you know, if you are studying the channel at T1 and T2 and the difference between T1 and T2 is much less than the coherence time of the channel, you can consider that the channel is highly correlated. You can push things to extreme and say, you know, the channel is constant, okay? So we can like sort of get, you know, adopt this assumption that the channel is almost constant over the coherence time. Okay, and so this will allow us just to, you know, to get rid of the T and just think of H, knowing that you know, after some symbols, you know, perhaps after 100 symbols or perhaps after 1,000 symbols, H will be a different value, right? Because again, things are continuously changing over time, but we are, you know, we want a tractable model. Okay, and so you know, just using H as a continuous time random process will be intractable, and so we do this thing here. So there is time. So there is a multipath effect. There is a multipath effect. It is just that the delay spread is much smaller than the symbol duration. There is dependence on time. It's just that we drop this dependence for convenience, okay? So don't let the model fool you. And again, this model is, you see in the many papers, okay? And references. Okay, so you have X, it's multiplied by H, and then of course, you know, you have basically this noise that is basically introduced into the signal by the electronics employed in the receiver, okay? And we will normalize things. So we will take the noise to be CN01, H CN01, so that's really fading. That's really fading. So if H is not zero mean, okay, if H is not a zero mean, then but it is still you know, Gaussian. So suppose that H is like, you know, Cn mu and 1 something like this. Then you have something called the Rice or Ricean channel model. And yeah, you know, you will encounter it in the problem sets. Okay, and we use a normalized constellation. This is important. Like when we later start, like basically simulating the system, you need like basically to stick to, you know, these assumptions. You know, the guys are independent of one another, and then, you know, if you make everything with unit variance, then where is the signal to noise ratio, right? So if you normalize everything, I mean, then you need like to have a constant that you know, that basically gives you the required signal to noise ratio. It is basically this factor here. So this is the average signal to noise ratio, and when you compute the powers, you apply expectation to magnitude H squared, magnitude X squared, magnitude epsilon squared. Don't forget that there is also something called the instantaneous signal to noise ratio. And the instantaneous signal to noise ratio is basically in this model, it is SNR squared, okay, and this is just SNR, magnitude H squared, and you don't apply expectation here, but you apply expectation to X, okay, and you apply expectation to epsilon squared, magnitude epsilon squared, so this will be SNR magnitude H squared. So this is the signal to noise ratio given the channel, okay. Average signal to noise ratio, you push things further and you also take expectation, you know, of the magnitude of H squared. Okay, assume we have binary PSK, you are interested in the average probability of error. It's a binary hypothesis testing problem, and now given H, we have basically this formula. So if there is no noise, again, what are our hypotheses? Okay, so what is, what is like the mean value of y? In other words, what is the mean value of y if x is plus 1 and if x is minus 1? Well, if x is plus 1, the mean value of y is square root SNRH. If x is minus 1, the mean value of y is minus square root SNR multiplied by h. So those are the means of the two hypotheses. Under both hypotheses, we assume that the noise variance is the same and is equal to 1. And in that case, the average probability of error will be given by the Q function, square root the distance squared, just the Euclidean distance squared, divided by 2. Okay, so the distance here will be, what is the magnitude of square root SNRH minus square root SNRH, and so this will give you 2 square root SNR, the magnitude of H, and so this is the distance. You square it, you get 4 SNR, magnitude H squared over 2. Okay, and so here is basically the Q function. What is this thing? It's the probability of error, accounting for the additive white Gaussian noise, but fixing H. We are here conditioning on H. So we're typically interested in the average performance, because this H, over some short period of time, this magnitude H squared may be high, at some other period it may be low, and so on. So on average, you need basically to take this thing and do the expectation. Okay, and then there was a nice question during the previous lecture, which is, so we take this thing and multiply. So you take this thing, okay, and multiply by f of h, which actually, this will be a double integral actually, because h has a real part and imaginary part, or we multiply by the PDF of magnitude h, or multiply by the PDF of magnitude h squared. Well, you get the same result. Okay, but the most convenient thing is to basically multiply by to think about this thing as a function of the magnitude of h squared, and to multiply by the PDF of the magnitude of h squared, because it's just an exponential. So suppose that you use the PDF of the magnitude of h, you will write down the integral, and you will find that you are going nowhere, and you will do a substitution of variables. So that actually you convert the Rayleigh distribution to an exponential distribution, right? So you will find yourself doing this here. And sometimes actually I will give you a problem later in which you will do the averaging actually with the PDF of H itself. Okay, but it's a matter of convenience. I mean, basically those three will give you the same result. Okay, for now, we just multiply by the magnitude of by the PDF of the magnitude of h squared, which is the exponential function, which is this guy here. Okay, so in this course we will typically use an upper bound, but sometimes I will require you to basically to compute the exact probability of error. Okay, so to do the exact probability of error with something involving the Q function, what you do is this. Okay, you take the Q function, you rewrite it as an integral. It is, by the end of the day, it's the tail probability of a standard Gaussian. So it is the integral from this quantity to infinity e to the minus v squared over 2 dv, and of course don't forget this guy in the PDF of the standard Gaussian. And then you interchange the order of operation, because your integrand is real valued and non-negative, so you can do the integration in any order of your choice. And so this is what we did in the previous lecture. We basically interchanged the order of operation, and we integrated with respect to g first, because the integration with respect to g is very manageable. And then we got to this integration here, and now you get something, when you consider the 1 multiplied by this exponential, and because you are integrating from 0 to infinity, you get 1/2. You are integrating a PDF from, a PDF around 0 from 0 to infinity, Gaussian from 0 to infinity, and it is 0 mean, so you get 1/2. And what about the other integral I showed you last time? Basically, integration, which is like sort of a general idea, and perhaps you can use it in homework 3. And it's general, and it is basically that if you are integrating something, and you know that this thing it resembles a PDF. perhaps without the normalization constants. Okay, so if you look at this integral, you say, oh, this thing here is what appears in the Gaussian PDF when the Gaussian random variable is zero mean. And so you try to match, you basically try to do matching as I did in the previous lecture. Again, this idea is general and you can use it basically in other parts of the course. We showed that basically once you do this integration here via matching with the Gaussian PDF, you get that the average probability of error is given by this quantity, which is like, okay, I mean, what is this thing? Perhaps, doing an approximation will reveal the dependence of the average probability of error versus the average signal-to-noise ratio. And so basically we can use this approximation that 1 plus alpha to the minus 1 over 2 is approximately 1 minus half of alpha. And so if you do this approximation here, which is justified if alpha is much, much less than 1, which is the case when the SNR is much, much greater than 1. And the dominant analysis in this course will be high SNR. High SNR analysis is typically what we will do in this course. Okay, so like if I say nothing, if I give you a system and tell you to analyze it, the default is that you assume that the SNR is very large. Okay, and so using this, you get this thing here. 1 will go with 1, and you get this result here. So the average probability of error, it decays with the average signal-to-noise ratio. This is unsurprising. You expect that when you increase the average signal-to-noise ratio, you get a better performance in the sense of a reduced average probability of error. But there is something bad going on here, because the decay of BE with the average signal-to-noise ratio is 1 over the signal-to-noise ratio. This is much slower than, okay, so this here, so the decay much slower than the exponential decay encountered in non-fading AWGN channels. Though for what you learned in like course like 242 or in a previous course on digital communications, basically you stop at the Q function, right? You stop at the Q function. You do not have this averaging step. This averaging step is because of this multi-path channel and so on. If you don't have this multi-path channel, you do not do averaging, and you stop at the Q function. And the Q function basically it decays exponentially. But here we have a decay that is much slower. It is 1 over SNR. Okay? So, you may say, well, I mean, we cannot generalize this result because you did this result for a very particular channel. You assume the Rayleigh fading model. So here we did things with H that is Cn01. And so the magnitude of H squared is exponential 1. Who knows? Perhaps, perhaps things are better. Perhaps things are even better than the non-fading case if you change the distribution. So, you are right if you say that, perhaps it is just this distribution is giving this basically very slow decay. But we can get something better using another distribution. So the answer is no. And to be able to make basically a judgment for a general distribution, our friend here is Jensen inequality. Okay, so for a general simple constellation, the conditional probability of error will be something like this. Perhaps you will have a constant outside the Q function and another constant here inside the Q function. Okay, So, if you are using QPSK, QAM, and so on, so you'll find that the conditional average probability of error is exactly equal to this thing, or is upper bounded by this Q function with those alpha and beta constants. Okay. So in the fading case, you will not stop at the Q function. What you will do is that you will average over the magnitude squared of, so you will average over the magnitude squared of the channel. You can check, perhaps I may be basically saying nonsense, but I think like in the notes there is actually a detailed, demonstration that basically this function is a convex function. Okay, if not, you can simply differentiate it twice and show that the second derivative is non-negative. So this is a convex function. Okay, so Jensen inequality tells you that if phi is convex, then the expectation of phi of x, okay, the expectation of phi of x, okay, is greater than or equal to phi of the expectation of x. Okay, so that's Jensen. And so we can apply Jensen inequality, and we can apply the expectation to basically to the argument, which here is G. So let's look here. What is going on? So the average probability of error for the fading case is always probability of error, bad. It's something that is bad. It is always greater than or equal to basically the same Q function applied to the average here. So what we can say is that for any fading distribution, the average probability of error will be higher relative to the probability of error in a non-fading scenario in which the channel gain is fixed and it has an average value equal to the average gain in the fading case. Okay, so if you compare, so you have a fading case, okay, and a non-fading case with the same average. Okay, so if you do this comparison to be fair, so we have a fading case, okay, so this is fading case, and non-fading with constant amplitude or magnitude, with constant gain, channel gain. Okay, it's always the case, so fading, it's always the case that the average probability of error here is greater than or equal to basically the error here, probability of error. And our friend here again, Jensen inequality, and the nice thing about this one line proof is basically it is, if you think that the above result is just due to Rayleigh fading, no. Fading is bad. Fading is bad, okay, but I need to be very, very specific, okay, because later in the course, actually we can have scenarios in which fading is good. So remember that I am in a scenario that is sort of very basic. I am talking about a single link, two users, a transmitter communicating with the receiver. No MIMO. I mean, it's the SISO case. We have, we have not yet introduced multiple antennas on basically the transmit or receive sides. Okay, so the conclusion here, not to overstate it, the conclusion here is that if you are in a scenario, single link, single user, okay, and single antenna, okay, then you can, yes, you can make the claim that fading is bad. It degrades your performance perhaps significantly. The average probability of error, rather than decaying exponentially, it will decay as 1 over SNR. Okay, so, but don't forget these things, because once you change the assumptions, if you have multiple users, or if you have multiple antennas, then the game will be different, and sometimes actually you can exploit fading, okay? Exploit fading to your advantage. You can make something good out of it, okay? But if you just stick to a single link, single user, single antennas on both sides of the communication link, then fading is bad. Any questions? So I told you, getting the exact expressions for the average probabilities of error sometimes can be very, very tedious, perhaps impossible. And so in this course, we will mainly go for an upper bound. And our friend here is this inequality that you may know from before of the Q function. So basically, if eta is greater than or equal to 0, Q of eta is less than or equal to exponential minus eta squared over 2. Okay, so this is very important. Keep this in mind. This is something that we will use a lot. Q of eta is less than or equal to exponential minus eta squared over 2. If you have done the proof, actually you can show that Q of eta is less than or equal to 1/2. Okay, so there is a 1/2 here. Actually, you can show in your proof, but we will drop it. Okay, so this is what the upper bound that we will use in this course. Okay, so we do not need like this clutter by this 1/2. Okay, so let's go back to our conditional probability of error. It looks like this Q function. Rather than integrating the Q function, let's upper bound it. Okay, so the upper bound is that you square the argument of the Q function and then you divide by 2. So when you square, this will be 2 SNRG, and you divide by 2, so you get basically this thing here, exponential minus SNRG. Now the average probability of error is a very, very easy integral, because now you are basically averaging this. You multiply by e to the minus g, and this is a very easy integral, right? You are integrating just an exponential function. Okay, and so the result is 1 over SNR, which is 1 over SNR if SNR is very, very high. Note that on the previous page, the result after assuming that the SNR was very high was like 1 over 4 SNR. Okay, so here we are upper bounding. It's like the factor 1 over 4 is not really worth it. Okay, but see the difference. The difference is, so on the previous page we did an exact computation and it was not so fun. Right, we had basically to interchange the order of operations and then do some integral using a matching with the Gaussian distribution, and then we had to use Taylor expansion, right? So we used basically this thing here, right? Now we don't have to do these things. Okay, if you just upper bound the Q function, you get the same trend. So sometimes we just focus on the trend. Here I just want to know that, how the average probability of error varies with the average signal to noise ratio. Okay, so makes your life much easier. However, some problems, I will tell you explicitly, in some problems I will tell you, please compute things exactly. Compute the integrals involving the Q function exactly. After you get the result, to do Taylor series expansion, and I will give you the number of terms to do in this, and so on. Okay, so hopefully you will be exposed to all these things. Okay. Now, in systems with multipath fading, like our system, typically the average probability of error will appear in this form: some constant divided by the SNR raised to the power d. So for this lecture, d is equal to 1, right? Because we got the average probability of error proportional to 1 over the SNR raised to the power 1. So in a chapter, so basically in a coming chapter, we will try to solve the problem of fading via diversity techniques. Okay, I will talk about this later. And so we will be able actually to make the average probability of error decay as the SNR raised to a higher power. Okay, so in some system you can get the average probability of error as k over the SNR squared or the SNR cubed and so on. But for basic fading, without employing any diversity technique, as we will see later, you just get this exponent here equal to 1. This exponent here has a name. It's called the diversity gain of the system or the diversity order of the system. Okay, so in this course, when you do the average probability of error, and typically we will go for the high SNR regime, you will get your average probability of error as some constant divided by the SNR to some power. This power, the higher this power, the better. Now, regardless of this power, you do not get an exponential decay in the average probability of error. However, 1 over SNR to the power 10 definitely decays much faster than 1 over SNR. So later in the course, actually, there will be a chapter in which the objective is to take this 1 here and make it a higher number. And of course, there will be a cost. Okay, so we will try basically to raise this power via diversity techniques. Okay, generally you will get the average probability of error as a constant over SNR to the D, and D is the diversity order or diversity gain. Sometimes I will use the term diversity order, sometimes diversity gain. They are the same thing, and it's a fundamental, basically a quantity in wireless communications. What is the diversity order, or what is the diversity gain of the system? Any questions? Okay. Let's be a bit practical. In reality, so on the previous couple of pages, it's like, you are doing the analysis, assuming that you know the channel at the receiver. You know it. Okay, so when you solve the binary hypothesis testing problem, you are basically, you know H. But in reality, you don't know H. And H, again, don't forget, H is actually H of T. It's a changing over time. It's just as a matter of convenience, we are dropping the time dependence. So we need to track the channel. We need to basically estimate the channel and do the estimation basically sort of in a periodic fashion. Every now and then we will need to estimate the channel because the channel is actually continuously changing over time. But I will now focus on the channel basically over a bucket of symbols that has a duration small compared to the coherence time of the channel, and so we can assume that the channel is just fixed. Okay, so here is basically our system. We will transmit a bucket of M binary PSK symbols. The first L symbols will not carry information. They are just pilot symbols or reference signals that are specified by the standard in actual communication systems, and they are known at the receiver. Okay, so here I will just go for +1s. So we will send L pilot symbols or reference signals. Reference signals is the term that is used in LTE systems. If you read the LTE standard, they refer to the pilots as RS, reference signals. So we will have L pilots, okay, and then we transmit our data. By the end of the day, channel estimation is done, so that you are able to detect the actual data. So now, then we will transmit data. So X L plus 1, XL plus 2 until XM, and so those are basically M minus L binary PSK information or data symbols. Okay. Now, what is basically the received signal model? Nothing fanciful. I mean, we agree on our signal model. So for the pilots, YK, where K is from 1 to L, you get square root SNRH, and here is 1. Okay, I omitted the 1 here because we agreed that basically the pilots will all be fixed at +1. Okay, so all the symbols are 1, and then of course we have the additive white Gaussian noise. But then when K is the received signals corresponding to the transmitted symbols from L plus 1 to M, those will have XK. Now there is an unknown binary BSK symbol that is to be detected, and of course there is the additive Gaussian noise. Okay, so we have basically the model now written for the whole received bucket. So we have M received signals. The first L of them correspond to the transmitted bilots of +1, and the last M minus L of them, they carry data. Now, H is H. It is not H sub K because of the assumption that the duration of the whole bucket of M symbols is smaller than the coherence time of the channel. So we will basically simplify things by just assuming that the channel is constant during the transmission of the M symbols, the bilots followed by data. And so H will not be indexed. It's just a single parameter that we need to estimate and then employ in the detection of the data symbols. Okay. Noise samples are assumed to be independent of the data, independent of H, and independent of one another. Okay, so again, these are the typical assumptions. Note that the transmission of bilots is needed so that we can estimate the channel, but there is a cost, because now you are losing rate, you are using information rate. Right, so the information rate now, okay, so information rate is something like M minus L over M, because you transmit M symbols. However, the actual information is carried by just M minus L symbols. Okay, so this is the information rate, and as we will see, if you want your channel estimate to be better, you will have to increase L, but then you will have to decrease the information rate. Okay, so there is a cost. And every communication system has an overhead. So you can think of the bilots as a physical layer overhead. It's basically a resource that is wasted because you have to estimate the channel. So rather than transmitting information, you will have to transmit those known symbols, the bilots or the reference signals, so that you can estimate the channel and you are able to decode the information symbols. Okay. So first order of business, estimate the channel. So to estimate the channel, what I will do is I will rewrite, so write those L equations in a vector form. Okay, so I will combine those guys as a vector, square root S and R, and then I will have a vector of ones. I will call it D, and then H, and then a vector of noise components, like this. Okay, so this is basically a vector of the received signals corresponding to the transmission of bilots, which are known. Okay, so we can write Y in this form here. And so what is the distribution of Y given H? So it is simply the distribution of the noise vector, right? But with a mean value. So this will be complex normal. The covariance matrix is IL by L. Our assumption again, those guys are independent of one another, and they are normalized so that each guy has a variance of unity. The mean value will be square root S and R. D, which is this all one vector, H. Okay, so that's the likelihood function. That's the likelihood function. It's complex Gaussian with this mean here, which depends on the channel H, and with a covariance equal to identity. Okay, so write down the likelihood function. Okay, so this is the likelihood function given our assumption. Okay, so this is the likelihood function actually to be correct, conditioned on H or given H. We are treating H here as a constant. And so how can we estimate H? Well, I mean, you have so many estimation techniques. So in the lecture, I will do maximum likelihood estimation, and in homework 3, you will basically obtain the LMMSE estimator for H. Okay, so here I will do ML. So ML is basically that you find H that maximizes the likelihood function, or you can just go for the log likelihood function, and because of the negative sign here, we can find H that minimizes basically this L2 norm squared. Okay, so the maximum likelihood estimate in our particular case here is H that minimizes the L2 norm squared of Y minus square root SNRDH, which is basically, I will call this thing here, I will call it a J. Okay, so how do we solve this problem? Well, we have here an optimization problem. Okay, so the objective is real valued is scalar, is a real valued scalar. What are our optimization variables? Our optimization variables are the real part of H and the imaginary part of H. Okay, and so what you can do is you can partially differentiate with respect to the real part, partially differentiate with respect to the imaginary part, and then equate to zeros. This function is actually a convex function, and so basically partially differentiating with respect to the optimization variables and equating to zero. In our case here, it's sufficient. It's sufficient for optimality. Okay. You know, one thing we can do is, you know, suppose that you get the partial derivative with respect to the real part, you get the partial derivative with respect to the imaginary part. Rather than equating each one to zero, we can combine them as a complex quantity like this and equate to zero. The idea here is simple. You know, if a complex number is equal to zero, then the real part is equal to zero and the imaginary part is equal to zero. Okay, so you can just compute this thing here and equate it to zero. In fact, you know, our H here is just a scalar complex number or complex quantity, but you know, later in the course we may have like a complex vector. So how can we obtain those partial derivatives sort of efficiently? It makes no sense that you actually expand this L2 norm squared and then write down each complex number as, you know, or variable as a real part and imaginary part. It will be very messy, very tedious. So how can we obtain the partial derivatives? Like, we want shortcuts. Okay, so in case you are basically differentiating with respect to not just one complex optimization variable, but you have k of them. Okay, so here we have 2k real parameters, which are the real of gamma 1, the imaginary of gamma 1, the real of gamma 2, the imaginary of gamma 2, and so on. How can we obtain this vector in like sort of one step? If you take a vector and equate it to the all zero vector, you know, it's basically you are equating each component to zero, and by equating each component to zero, you are basically equating each partial derivative to zero. Okay, so if there is a trick to get this gradient vector, like sort of in a magic way, just equate it to the 0k1 vector, and it's as if you are computing the partial derivatives with respect to the real parts and imaginary parts, and then equating all partial derivatives to 0. Okay, so here are the rules. And their derivation, you can derive them. They are not difficult actually to derive. So these rules are your friend. They are very important. Keep them in mind. And they are useful in this course, and they are useful also for those taking the math course. Okay. So Q is a given vector, and big gamma is basically the vector carrying the optimization variables. So suppose, in many optimization problems, you will get something like this: a known vector, and you get the inner product of the known vector and the vector of optimization variables, and you get the complex conjugate of this guy here. Okay, and so suppose you want to obtain this vector. Again, because what is this vector? It's a vector, carrying the partial derivatives, and if you equate it to the O0 vector, you are basically, equating each partial derivative to 0. So how can we get this vector directly? So this vector in this case is simply 2q. It is simply equal to 2q. Another form that is we will encounter a lot is a quadratic form with a Hermitian matrix. Okay, so in this case, the gradient vector will be 2a gamma. And then, if you have an L2 norm squared, which is basically what we are doing here, so you have the L2 norm squared b minus a gamma, L2 norm squared. So what if you want to get your gradient vector like directly? So it is, so here is the trick. Write down the thing here, the vector with respect to which you are computing the L2 norm squared. Put it between brackets, and then minus 2 the Hermitian of this matrix. Minus 2 the Hermitian of this matrix, and if your stuff is just real valued, this will be A transpose. Okay, so in my case here, this is what we have, and so what is the partial derivative? Okay, so again I will do it. It's written here, but let me do it. It will be, I will write this thing. We want basically this quantity here. It happens to be just just a one by one complex quantity, but generally it will be a vector. Okay, like this, and then we have minus 2, and then we have the stuff. So this is our optimization variables are living here. We just take the the thing multiplied by each and take the Hermitian. Okay, and so this is just a constant. And then you take the Hermitian. It happens that basically this D is the all one vector, and so the Hermitian is just D transpose. Okay, and so we take this thing and equate it to 0. If you take this thing and equate it to 0, then you are equating the this guy to 0 and that other guy to 0. Okay, if you're interested in how these guys are derived, I mean, I can send you like notes or something like this. Okay, so basically for much more. There is something, an online resource that is very useful, and there are other books, but I will just mention the online resource called the Matrix Cookbook. Okay, I wonder if you're doing research and you will not open this guy. I mean, it's you will typically have to open it from every now and then. Okay, so if you don't find something here and it's not in any other reference, you will actually have to get your result. And so sometimes it's actually useful actually to know how these guys are derived. I mean, in case you encounter you have in your research problem something that is like sort of not there in the literature. Okay, let's go back to our problem. So equating this thing to 0, then we have d transpose y. Remember, what is d? D is the all one vector, and so this is 1s multiplied by y, which is like this. So those are the received signals corresponding to the pilots, and so d transpose y is basically the sum of the received observations corresponding to the pilot symbols. And we will get here d transpose d, and if you multiply d transpose d, you just get 1 plus 1 plus 1 L times, and so you just get L. And so your maximum likelihood estimate, again here I am writing that, I am assuming that when you partially differentiate and equate to 0, you get the optimal result directly. Okay, and again, yes, this is the optimal result because of the objective function in our problem. The objective function in our problem actually is one of those objectives for which basically it is, just computing the partial derivatives and equating to 0 is sufficient for optimality. Okay, and so more details. I mean, I know most of you are taking also the optimization course, and some of you are taking the math course, and so these things will be discussed there. Okay, but yeah, you just need to here to differentiate and equate to 0. And if you want to compute the Hessian matrix, you will find that the Hessian matrix is basically positive definite, indicating that actually you have obtained the okay. So so here we did ML estimation, and the ML estimator, if you look at it, is basically what it tells you. If you want to estimate the channel, basically do a summation over all the received signals corresponding to the transmitted pilots, and then divide your summation by L, which is the number of pilots, and then by this factor here, which is square root SNR, and you will get an estimate for the channel. Okay, so next I will basically investigate this estimator. Okay, because whenever you have an estimator, you want to know, for example, is it biased, unbiased, consistent, inconsistent, and so on. Okay, so I will do this on the next page. Any questions?
Professor?
Yeah.
Is there any rule on how to choose the number of pilots to achieve a certain performance, for example?
Yes. I mean, you can optimize actually over the pilots, because like you can write down a problem. In which you basically have an objective that accounts for the average probability of error in your system, and also the loss in transmission rate due to the pilots. Okay, so you can say, oh, I mean, I am basically getting this performance, but also I am from M symbols, I am using L symbols for channel estimation. Okay. And so you can get an objective function, and you can optimize. You can actually try to find what is the optimal number of N. Okay, so that's true. Okay, so we can optimize over L. I will not do this here, but like especially in MIMO systems, this is like not a big issue in SISO, but in MIMO systems, because you have so many channels to estimate. There is a channel between any transmit antenna and any receive antenna. There are so many channels, and so the issue of pilot optimization becomes very relevant. Okay, and so yeah, you can find papers about pilot optimization, and this may include actually the number, basically the optimal number of pilots. Again, why do we have sort of an optimal number of pilots? What is the intuition? The intuition is that on the one hand, as we will see, if you increase the number of pilots, you have a better estimate for the channel gain, and you have better detection performance. But on the other hand, you are reducing the transmission rate because you are transmitting symbols carrying no information. Okay, and so you may think that there is sort of a sweet spot, so you don't want too many pilots. Okay, too many pilots means a very good channel estimate, but a significant reduction in the information rate. And if you use very few pilots, your channel estimates will be very noisy. And then basically your performance in terms of, let's say, the probability of error will be degraded. Okay? Here in this problem, I'm sort of fixing L. So this is a recap of what we have done. Basically, we wrote down basically the received symbols corresponding to the pilots. We obtained the maximum likelihood estimate, and it is given by this. Now we ask ourselves, so the estimator itself depends on the observations, right? And the observations are contaminated with noise, and noise is very random, right? So in other words, like if you do the estimate now, suppose that the channel is truly fixed. If you do the estimates now, you get a number, after a while you get another number, even if the channel is fixed, because you have the noise, the additive white Gaussian noise. So the estimator itself is a random variable, and its mean, so take the expected value, okay? If you take the expected value, so expectation of given H is basically the expectation of 1 over SNR L D transpose Y. And so this is 1 over square root SNR L D transpose expectation Y. Okay. And Y given H, if you want to be super accurate. Okay. What is the expected value of Y given H? It is just this first term here because the noise is 0 mean. Okay, so plug in the expectation of Y given H, and you will find that basically what you get here, this will cancel with this, D transpose D is L, L cancels with L, and you get H itself. Okay, so you know this from a previous course, that if your estimator has a mean value that is equal to the parameter to be estimated, okay, then we call our estimator an unbiased estimator. But more importantly, here basically will be the variance of the estimator, which gives you the quality. So what is the variance of our estimator? So again, our estimator is a random variable. It will not give you, again, if you repeat the experiment under a constant H, you will always get different results due to the contaminating noise. And so we want to, a good estimator will have a small variance, and hopefully the variance will go to 0 as L goes to infinity. And so this is the property of consistency. And so you compute the variance. So what is the variance of the estimator? So in the previous step, we showed that the estimator has a mean value of H. So subtract the mean value from the estimator, take the magnitude squared, and so apply expectation. Okay, so here we apply the expectation. Now it's very important, I have seen this in the homework, sometimes some of you basically you have a complex quantity and you deal with it as a real quantity, okay, which is very dangerous, right? So, for example, a variance of a complex valued random variable is in terms of the magnitude square, not the square. The square of a complex quantity is generally a complex quantity. Okay, but the magnitude square is real value and non-negative, right? So basically the variance of a complex valued random variable, it is magnitude squared. Okay, very important. You cannot just put it square. It's not even a correct definition. Okay, and it will give you a funny variance that is a complex number. Okay, so you need the magnitude squared. Okay, and the magnitude squared is the random variable multiplied by its complex conjugate. And the random variable here is a scalar, so the conjugate is like taking Hermitian. Okay, so because it's just a scalar. And now let's what is so we are trying to write things in terms like of HML minus H and then the Hermitian. So what is this thing here? What is HML minus HML minus H? Okay, so this is 1 over SNR L, okay, D transpose. What is Y? Y itself is square root SNR H, right, plus epsilon minus H, okay? And so you get here what, sorry, there is a D here, okay? So what you get here is equal to 1 over SNR square root L, and then D transpose D gives you another L, and then this guy gives you SNR, and then you have H. So those guys will cancel this H, so this will be 0, and you are left with, basically, you are left with, so this will be 1 over square root SNR L, D transpose epsilon. D transpose epsilon, okay? And so you take this vector and you multiply it, so you can think of this again as it's a 1-by-1 quantity, but the trick here is to it as if it's an outer product, because this will allow you to basically make use of the covariance matrix of vector epsilon, the vector of the additive wide Gaussian noise. So again, you multiply this thing by its Hermitian, so you get 1 over SNR L D transpose epsilon, and then you multiply by D transpose epsilon. You can put conjugate, you can put Hermitian, it's just a scalar quantity, and so this becomes epsilon Hermitian. D transpose Hermitian is just equal to D. Okay, so that's basically this expression here. And now you can apply the expectation. What is random here? Nothing is random except the vector epsilon of contaminating noise, and its covariance matrix is ILL using our model. And so basically you are left with D transpose D, which is L, and so the variance of the estimator is 1 over L divided by SNR, which is sort of like intuitive. Like this result tells you that you get better estimation performance, okay, better basically in the sense of getting a reduced estimator variance if you increase the average signal to noise ratio, or if you increase the number of pilots. And this is intuitive, right? If you increase the number of pilots, or if you increase the average signal to noise ratio, then basically you are getting better estimates. Okay, if there is no contaminating noise, if SNR is infinity, you basically nail it. You know exactly what the channel is. Okay, so basically this expression is sort of intuitive, and as you can see, it goes to 0 as L goes to infinity. Okay, it goes to 0 as it goes to infinity. So what we have is that limit L goes to infinity of expectation magnitude HML minus H squared. This thing is equal to 0, right? So basically HML as a random variable, it converges in mean square to H, and because this is the definition of mean square convergence, and mean square convergence implies convergence in probability. So HML converges in probability to H, and that's the definition of the consistency of an estimator. And so actually our ML estimator here is also consistent. It's unbiased and it is a consistent estimator because the estimator converges in probability to the true value to be estimated, which is H itself. Okay, so this is like sort of an investigation of the estimator, but now you don't estimate just for the sake of estimation. Some people do this. If you want to study, if you want to do channel modeling and so on, you estimate the channel just to know distributions, correlation functions, and so on. But here, this is an actual receiver with the objective of decoding the data symbols. So now we want to detect, we want to know, the symbols are +1 or -1 if we are transmitting binary PSK. Now, in the previous lecture, if you know H, this is the detection rule, right? So remember, we wrote it like this, or you can write it as the real part of H conjugate Y, and you compare it with 0. If greater than 0, we have +1, less than 0, we have -1. So what should be your detection rule now? So as a receiver, what do you know at the receiver? You know Y. Now this is YK that corresponds to one of the transmitted symbol. You know it. It's basically the received signal. And you don't know H, but you know its estimate. And so the way to go is to use this same rule, replacing H by what you know about it. That is to say, replace H by its estimate. Okay, so what we will do is that here we will use the estimator. Okay, so here we use the same detection rule, but employ our estimate of age. Can we do something else? I mean, by the end of the day, we don't know the true channel, right? So, I mean, this is the way to go, right? So you just use the channel estimate, and this becomes your detection rule. So it involves now the channel, the channel estimator, the estimated value of the channel, and of course the received signal corresponding to one of the transmitted binary BSK symbols. Okay, and so I will call this thing here psi, and we will compare psi with 0. If it's greater than 0, we say +1. If it's less than 0, we say -1. Okay. Now, can we make an error? Yes, we can make an error. For example, if psi is greater than 0, but so you will say that the transmitted symbol is +1. So if the transmitted symbol is -1, that's an error. Okay. And this is the error I will focus on. The other error is symmetric. Okay, so basically, typically you compute this error. So this is the error that you say +1 while it is -1. There is the other error in which it is +1 but you say -1, and then you multiply each by a half for equiprobable, basically plus or -1, and then you add. But here, I mean, you can check it for yourself. Basically, the two probabilities are the same, and so I will just focus on one of them. What is the probability that psi is greater than 0? But now, as I said in the previous lecture, I mean, we have like now the additive white Gaussian noise. That's random. We have H, the true channel, and also we have the estimator of H, which is itself a random variable. Okay, things here are messy, and so the way to go, this is the philosophy. You will find it basically throughout the course is, let's first tackle the additive white Gaussian noise, assuming that H is fixed, and in our case here also assuming that H hat is fixed. Okay, so we will start by basically fixing or conditioning on H and H hat, and we will compute, basically the probability of error. And so, probability of error due to what? Due to the Gaussian noise. And then after that, we will do the averaging. Okay, then after that we'll say, no, H is a random variable. H hat is a random variable, and basically, let's use their distributions to obtain the average probability of error. Okay. Now, Q function. Q function will basically, you can do it, but when you come to the averaging step, you will not be able to go anywhere. So we want an upper bound. Okay, so upper bound, and here I will use the Chernoff bound. So we will go for facilitate the next averaging step. Okay, I will use here Chernoff bound. Okay, so basically, what is the, here we are, I'm conditioning on those guys. I'm conditioning on H hat, and X k is -1. So what is the probability that a random variable is greater than something? Multiply both sides of the inequality by a positive parameter. Okay, this will not change the equality. In fact, this event is equivalent to that event because rho is strictly positive. Then the exponential function is increasing. So apply the exponential function to both sides. So e to the rho epsilon, rho psi is greater than 1. okay, and then this is a non-negative random variable, and so you can apply Markov inequality, and so this quantity is less than or equal to the expectation of the non-negative random variable divided by this guy here, which is just 1. So this is the upper bound. Okay. So generally, when you do the Chernow bound, then you have like varieties, right? So you have the option of minimize with respect to rho to get the least upper bound. Okay. Or sometimes this is not feasible. Further upper bounding, then minimization with respect to rho. Another option, you will see it in many problems. Or just set rho to a convenient value. Okay. So maybe there are other options, but I mean, this is what you when your upper bound a tail probability. You typically, if you go for the Chernow bound, you introduce this positive parameter, and then you either optimize over it directly, or you may actually need to do further upper bounding depending on your objective, or sometimes you just see, this upper bound. So basically, this upper bound is valid for any positive rho. This upper bound is valid for every rho that is greater than 0. So let's just choose a rho that is nice. Okay. So in this lecture, what I will do is basically option 3. I will I will not do any minimization, and I will just set rho to a value that makes things easy. Now, when you do the Chernow bound, you typically hit the moment generating function of the random variable. Okay, so basically we need to know what is this moment generating function in our particular case. Note that when we condition on h and h hat and xk equals -1, then basically hello, yeah, and then basically this psi becomes conditionally Gaussian. Okay, so this is psi. Remember, psi was like h hat conjugate multiplied by yk plus h hat multiplied by yk conjugate. So plug in those guys. Okay, and put x k equals -1. We are conditioning on that, and basically psi is conditionally Gaussian. See why it's conditionally Gaussian? Because those guys are assumed to be constant, and we just have those guys. If you add these two guys, you get the double the real part of the additive white Gaussian noise. And what is the distribution of this real part? It is Gaussian. Okay, and so basically psi is conditionally Gaussian. And the idea now is, what is its mean? What is its first moment? And what is its variance? So when you take the mean, those noise components are 0 mean, and so this is the mean value, conditional, of course. So conditional on h hat, and that xk is equal to -1. And what is the variance? Okay, so for the variance, this part here is a constant. So when the variance of a random variable plus a constant is exactly equal to the variance of the random variable. So now you want to basically get the variance of what? So you want the variance of h hat epsilon k plus given. So this is homework 2 problem 3D. Basically the idea here, okay, and I will tell you the solution because it's important and relevant to other parts of the course, that you have here epsilon k, which is circularly symmetric 0, 1, and so it's circularly symmetric, it is proper, and this is its complex conjugate. So it turns out if you have a random variable z and you have AZ plus BZ conjugate, and if Z is proper, okay, if Z is proper, then Z and Z conjugate are actually uncorrelated. Okay, so if Z is proper, Z and Z conjugate are uncorrelated, which is so nice when you compute the variance, because when you compute the variance, you know, of a sum of two random variables, it's the variance of the first plus the variance of the second, and then plus the covariance, right? But the covariance is 0 because the guys are uncorrelated. Okay, so this is the first thing to put in mind. If you have a random variable, complex random variable, that is proper. It must be proper. If it's proper and you add to it as a complex conjugate, the two guys are uncorrelated. So when you compute the variance, you can just compute the variance of, you know, the first term here and the variance of the second term here. Okay, so this is very nice. The second thing is that if your stuff is complex, so the variance of AZ, so complex stuff, then it is not A squared, it is the magnitude of A squared. Or magnitude A squared, I mean, or magnitude A squared. Okay, this is equal to that, and then the variance of Z. Okay, so this is very important. So, so here, this is exactly what I will do. I will take, okay, so what is the variance of this quantity? So it will be the magnitude square of this guy plus the magnitude square of this guy, and again, epsilon and epsilon conjugate, they are uncorrelated because of, you know, the result in this problem set. And of course, the magnitude of a conjugate of h hat is exactly the magnitude of h hat itself, and so we can combine these two guys as double the magnitude square. And so here is the conditional distribution of epsilon given h hat and xk equal to -1. This is the mean, the first moment, and this is the variance. Of course, you know, I am writing it here. It's a real valued Gaussian. It's a real valued Gaussian because epsilon itself, you know, you have it like it is a complex valued quantity, right? Epsilon is h hat, right? And then y plus h hat conjugate y, and then h hat y conjugate, right? So you are adding a conjugate to the complex quantity. So epsilon is indeed a real value. So it is a real value Gaussian with this first moment and this variance here. Okay, so back to our Chernow bound. So the Chernow bound, again, you typically end up with the moment generating function. So this is the conditional moment generating function, and when you condition on those guys, epsilon again is Gaussian, and you get its first and second order statistics. You know it from a previous course, or you can open Wikipedia or open any reference. What if basically if you have a random variable, let's say phi, and it is a normal, and it is here m and sigma square. It has a standard form for its generating function, and I don't think it's difficult to prove. It is exponential, so expectation of e to the row phi is basically e, and then you have m row. Okay, so you multiply row by the mean value, and then plus, and then you have 1/2, and then you have sigma squared, and then you have row squared. Okay, so there is a standard form for the moment generating function of a Gaussian. Just go and take it from any reference, and you put it here. Okay, so we'll use the, you can see that the moment generating function, it requires that you know the mean value, and it requires that you know the variance, and so we know the mean value and we know the variance, and so plug them in, and this will be our conditional moment generating function, which is an upper bound on this probability of error, because again it's a probability of error because xk is -1, but if the decision statistic exceeds 0, you will make a decision in favor of +1. Now, as I said, what should you do now? If you optimize over row, you will complicate things, and averaging later becomes impossible. And so the way to go is simply to just put row equal to a convenient value. And the convenient value here will be that row is equal to the square root of S and R. It makes things very easy. And so the motivation here is this. You have a square root S and R here, and row, and here you have row squared. Okay, and if you just put row equal to square root S and R, by the end of the day, the upper bound is valid for any positive row. You can put row as you wish. So if you choose it to be square root SNR, you can take SNR, the average SNR, as a common factor, and then you find that like sort of your random variables appeared in a way that you can easily manipulate. Okay. So now we have, so this depends on, so this is the conditional probability of error, depends on what? Depends on H, which is the true channel. The true channel comes from the expression for Y. Whenever you received a signal, it passes through the true channel. Okay, so that's the reason you have an H. Your received signal corresponding to a symbol is HXK, H the true channel. But the detection rule basically tells you that you should take this received signal and you multiply it by the conjugate of the estimator, and then you basically do the other term. So you also have the estimator. Okay, so let's basically write H bar. So we write H bar as H minus gamma. Okay, so here it's like gamma is like estimation error. So what I will do here is to rewrite things. I will do like a slight change. I will depend on H and gamma. Okay, so H and gamma, because you can go from H and H bar. You simply take the difference between these two guys, and the difference actually has a meaning. It is the error in your estimate. It's the difference between the true H and the estimated H. So you can write down things in terms of H and gamma. And when you do so, you expand, right? Because you have here the magnitude of H squared, and so you have this magnitude squared, and so it's the magnitude squared of the first guy plus the magnitude squared of the second guy, and then you have cross terms and so on. The nice thing is that the cross terms will cancel, and you will get a separable terms, a term that depends only on the magnitude of H squared, and a term that depends only on the magnitude of gamma squared, where gamma is the difference between H and the estimator of H. Okay, so basically we can just work with the magnitude squares. Let's call this guy G, and let's call this guy eta, and this is our function. So this is conditioned on G and eta, and G again, don't forget, G is magnitude H squared, and eta is the magnitude of H minus H hat squared. Okay, and this is an upper bound, and in many cases, especially at high SNR, again, we go for upper bounds. Now we need to do averaging. Well, tell me the distribution. I mean, what is the distribution of G? Well, G is magnitude HR squared. If H is a circularly symmetric complex, standard CN01, then G will be exponential 1. So that's, the thing that we did earlier in the lecture. Nothing mysterious here. What about eta? Eta is basically the estimation error, or the magnitude squared of the estimation error. We studied the estimation error, right? So the estimation error itself, remember, H hat minus H. Okay, we basically studied this quantity, is zero mean. It is zero mean. Right? Why it's zero mean? Because we proved that H hat is an unbiased estimator. So its first moment is basically equal to H itself. So it is zero mean, and we computed this variance. Variance is basically 1 over SNRL, that I did above. And so basically gamma itself, which is the difference, is a complex normal, circular symmetric, 0, and the variance is 1 over LSNR. And so if you take the magnitude square of this guy, you will get eta, which is exponential LSNR. So exponential with a parameter which is LSNR, right? Because it is, so here in this course, okay, the notation, it may be important, like if I write exponential lambda in this course, lambda is 1 over the mean value. Okay, so here in this, in ACE 244, this is the exponential distribution. Lambda is not the mean. Lambda is 1 over the mean. And the PDF is lambda exponential minus lambda. Let's say alpha greater than or equal to 0. Okay, because some people, when I write exponential number for exponential 1, I mean it doesn't matter, but exponential 2 is the mean value 2 or 1/2 and so on. So here again I stick to this definition for the exponential distribution. The parameter here is the reciprocal. Okay, is the reciprocal of the mean. That's it. Okay, so we want to do the averaging, and of course we will assume that the guys are independent. The channel, I mean, remember that the estimation error is because of the noise contaminating the observations corresponding to the pilots. While this is the channel itself, this is magnitude h squared, are assumed to be independent, and so when you do the averaging, you can just average on this guy and then multiply by the average of this guy here. Okay, so I should actually write here an expectation. Okay, so yeah, I should, sorry. So this is basically given G and eta, and here I need to read the average. I need to write down average BE, okay, is equal to, so now we do the averaging, we do each average on its own. So here we multiply by the PDF of G and integrate, and here we multiply by the PDF of eta and integrate. Note that when you have the PDF of eta, see these two exponentials, if you combine them, it becomes minus SNR eta L minus 1. Okay, now if L is equal to 1, if you transmit just one pilot symbol, this will be e to the 0, which is 1, and this integral will explode. So we need L to be greater than, strictly greater than 1. So our upper bound will basically shoot to infinity if we put L equals 1. And so we need, like, basically for this integral to converge, we will need L to be strictly greater than 1. Then we have basically a decaying exponential, and this is its integral here. Okay, and our upper bound is this quantity. You get from the first term 1 plus SNR again. If SNR is very high, we can just use 1 over SNR, and this is our result. Okay. So it's a very nice problem in which, like, we account for the multi-path fading channel, and also we account for the process of estimation. So in this case here, we accounted for the estimation errors, and the way we did it is basically we used the decision rule in case of perfect knowledge of the channel, and we said, this is real life. Nothing is perfect, and we just need to estimate, and we will use the same decision, and in the decision rule we will use the estimate of the channel. In that case, your conditional probability of error, it depends on two things. It depends on the estimator, and it depends on the true channel itself. So you condition on both, and initially you just tackle the additive white Gaussian noise. Here we didn't go for the Q function. We went for the Chernow bound. Okay, and then later, basically you average, and in our case here, see what is the impact of not knowing the channel. If you don't know the channel perfectly, what will happen is that, previously the upper bound was 1 over SNR. Now it is 1 over SNR multiplied by this quantity, which is strictly greater than 1. So if you put L equals 2, this is 1 over 1 minus 1/2, so this will be 2. So basically this is a quantity that is greater than 1, and it means that the upper bound here increases. And in reality, actually, the performance definitely will degrade if you use an estimate. Like, if you use an estimate rather than the true thing, definitely you will get a degradation in performance in the form of, say, increased probability of error. Okay, so definitely you want L to be like sort of large, such that this is reduced. But there is a problem. If you increase L basically to reduce the negative impact of channel estimation errors on the average probability of error, you are reducing the transmission rate. Because to increase L, you cannot, it's not a math problem, it's just a put L equals 3, put L equals 4. No, physically what you do is that you transmit pilots. you transmit more of them in a single data packet, then you are basically reducing the amount of information symbols. Okay, so you need a balance.